The next speaker is Prateek Kumar Vishwakarma from India Institute of Science, and his title is Plucker Inequalities for Weakly Separated Coordinates in Totally Non-Negative Grassmannians. So please.
Thank you so much. So thank you very much to the organizers for giving me the opportunity to participate and give a talk here. So this is a joint work with Daniel Soskin in which we discover certain determinantal inequalities that very naturally appear over the totally non-negative Grassmannians. So the origin of these inequalities is in matrix determinantal inequalities. So let me very quickly go through. Just recall, well, Misha has been discussing about total non-negativity very extensively, so I'll go through the details about the basic details very quickly. So let's begin. So we know that a matrix is called totally non-negative if all of its minors are non-negative. And in this talk we will use some very standard notation, so let me not read those. So for example, as an example, the type of inequalities that we will see today, let me discuss this example. So consider 4 by 4 totally non-negative matrices A, then expand its determinant along the first row, then and look at the last entry in this expansion. Now the last entry in this expansion is minus A14 times determinant A14, which is a non-positive quantity. So if we remove that term from this expansion, we get an inequality that holds for all 4 by 4 totally non-negative matrices. Now this was not very difficult to see. However, the phenomena sort of continues. That is, if we remove the next last term in this expansion, then in the second inequality, then again we get an inequality which holds over the 4 by 4 totally non-negative matrices. However, the sign of the inequality now has been reversed. The process continues. That is, if we remove the next term, we again get an inequality which is also known as the Fisher inequality that we saw earlier yesterday, which holds over all 4 by 4 totally non-negative matrices. So this phenomena of removing terms one by one from the Laplace expansion and getting inequalities was discovered by Gann-Marker-Krein, in which it was shown that looking at partial Laplace expansion along the first row for totally non-negative matrices yields number which is either greater than the determinant of the matrix or less than the determinant of the matrix, depending on the length of that partial expansion. So in my recent work with my former postdoc mentor, Sean Fallett, we were able to generalize that the inequality of Gann-Marker-Krein's by basically identifying similar oscillating set of determinantal inequalities by refining the generalized Laplace identity over the totally non-negative matrices. Now, as you can see that we were not able to incorporate all of the terms that are sitting inside the generalized Laplace identity. And other than this, we also had one of the other difficulty that we had was to figure out the orders in which the terms in the Laplace identity should appear so that the oscillating inequalities can be obtained. So other than this, we also looked at the Carlin's identity and we obtained the same result that these oscillating set of inequalities exist here for totally non-negative matrices. Now in this talk we want to see, and there were a few more other inequalities that I'm not discussing here. So the idea is to capture all of the theory of the theory that goes behind the existence of these oscillating inequalities out of identities for totally non-negative matrices. So for that we will look to refine the long Plucker relation itself over the non-negative Grassmannian. So let's recall that that Grassmannian M plus N is essentially a tall matrix of full rank modulo column operations. So and the maximal minors of those tall matrices give us Plucker coordinates, and these Plucker coordinates are very nicely related with each other via relations called Plucker relations. So let me now restate these Plucker relations in the way that we want to look at it. I mean, they are the same Plucker relations, it's just that it's a bit more convenient to state the results. So suppose I and J are M element ordered sets, and then we construct sets IKR and JKRs in which the element IR and JK replace each other respectively in I and J. Then the Plucker relations are just delta I times delta J is equal to sum over delta IKR times delta JKR. Now with the experience that we had in discovering those generalizing the Gann-Marker-Krein's inequality, what we want to do here is that we move the delta I delta J term conveniently on the right hand side at some so-called midpoint, and then also order the elements delta ikr and delta jkr, so that removing the elements in this order from the Plucker relation gives us those oscillating inequalities. So we will have to do two things. One is to figure out this midpoint and also the order in which the delta ikrs and delta jkr appear.
Can I stop you? I see a summation over k, but I don't see what r is in your first equation.
So r is any fixed number between 1 and m.
Oh, r is fixed.
Any fixed, okay. Yeah. So this is how we are looking to refine the Plucker relation. So, and we will do that over the TNN Grassmannian, and we know that TNN Grassmannian is just those tall full rank matrices in which the maximal minors are non-negative up to some non-zero constant. Now working in the TNN Grassmannian is enough to generalize the inequalities that we have seen so far, because the set of TNN matrices are sitting inside the TNN Grassmannian via this map in which the representative matrix A bar is just appended, is just A appended with the anti-diagonal signed exchange matrix W0, such that, and with this map there is a one-to-one correspondence between minors of A and maximal minors of A bar. So because of this and the projective geometry and the density theorem, we can have this result, which basically says that in order to study determinantal inequalities in products of two minors over TNN matrices, it's necessary and sufficient to study inequalities that are in products of Plucker coordinates for the representative matrix A bar, and equivalently one can also study the inequalities, determinantal inequalities that are in products of two Plucker coordinates over the non-negative Grassmannian. Now the reason we want to state this result here is because we know the classification of the second inequality, but we want to classify inequalities of the third type. So because these are equivalent, once we study the second type, the inequalities that look like the second type here, we know the third ones are also true. So let me now state the main result. So suppose m and n are integers, and suppose I and j are m element ordered subsets of m plus n. Now we locate these elements, the elements of I and j on the circle with points 1 to all the way to m plus n in the clockwise order. So we make the circle, we identify the points of I and j on that circle. Now if we can separate the elements of I minus j and j minus I via chord in that circle, then we call I and j weakly separated, otherwise they are not weakly separated. Now the concept of weak separability is very fundamental in defining the cluster algebras of the Grassmannian, and because Misha is here, maybe he would be able to talk more about these weak separability. Now suppose eta is the number of I minus j and number of elements in I minus j, and also the number of elements in j minus I. Now I sort of alluded to a certain order that we want to introduce to obtain these inequalities. So now we are going to talk about that order. So we order the elements of I minus j as I1, I2, I eta, and j1, j2, j eta for j minus I, such that in moving in the clockwise order, starting from I1, we encounter I1, then I2, then I3, and so on, and the end we encounter j eta. And similarly for the elements in j minus I as well, starting from I1, we should encounter I1 obviously, and then j1, j2, and so on up to, and the end we should find j eta. Okay, so once we have fixed this order, we define IKR and JKR, where the IR and JK replace each other in I and J. Now with this formulation, these are the inequalities that we found. So that are true over the totally non-negative Grassmannian. So what we are doing is that first of all, that midpoint that I talked about is given by index eta minus r plus 1, at which point the delta j term gets introduced to those system of inequalities, and this sign term outside is just to balance out the negative inequalities. And we also show that these inequalities hold for weakly separated sets and only for weakly separated sets. These do not hold for any other type of Plucker coordinates delta I, delta j. Now, if you want to look at these inequalities slightly in a rather homogeneous terminology, then again, as I said, we move the delta I, delta j terms and pair it with some delta ikr, delta jkr carefully, and we keep the rest of the delta ikr, delta jkr all by themselves, then we just have to take the sum over pi krs and multiply with the corresponding sign of the last element that entered the inequality. Then we get all of these inequalities, and again these hold for only precisely for weakly separated coordinates I and j. I see. And for weakly separated, when I and j are weakly separated, that is the cases that we saw earlier in which the sign of the inequality was alternating. If we order the elements in ikr and jkr in the increasing order and I and j as well, then the signs that come out are in fact alternating. So we can see that the inequalities that we saw earlier are in fact sort of sitting here. Yeah. So let me now discuss some proof ideas for weak separability implies the inequalities. So for that we look at temporally. So this was the idea due to Rhodes and Scandera. So we basically look at temporally algebra Tn psi to be which is the complex algebra generated by elements T1, T2, Tn minus 1 subject to these relations. So this algebra can also be seen as a quotient of Hecke algebra, but we don't have to go into that because we will eventually set out psi is equal to 2, which is just a quotient of the group algebra itself. Now the standard basis of this algebra Tn psi is just the product of all of these T1, T2, Tn minus 1 subject to these relations. And one way to look at the basis elements of Tn psi is to just look at the 3 to 1 avoiding permutations in Sn and identifying each of the Si's with Ti's. Now because of this, one can also see that the number of elements in the basis is exactly the Catalan number. Now let's for our application, for our requirement, we need to equate psi is equal to 2, and in which case we get an isomorphism between a quotient of the group algebra and Tn2 via the homomorphism that maps Si to Ti minus 1. So now that we have this homomorphism, we can define the function fk corresponding to each basis element for Tn2. So how do we define that? So fk omega is, so we can compute sigma omega. So in that sigma omega, we have the word S1, S2 and so on. So we basically multiply out T1 minus 1, T2 minus 1. So multiply it out, look for k in that multiplication. The coefficient there gives us fk omega. So we have defined fk for each of the basis element in the algebra, in the basis. And now we define the temporally imminent, which is given by this function, which is essentially the determinant. However, the sign term in the determinant has been now replaced by fk of omega. So instead of sine of omega, we have fk of omega. Now in particular, it's not very difficult to see that imminent corresponding to the unit element in the basis gives us the determinant, because when k is unit, sigma of omega is just the sine of or length of omega. So determinant is generalized by temporally imminence. And combinatorially, I mean, without going into too many details, we know that determinant counts counts non-crossing paths, families of paths. Temporally imminence counts a collection of generalized wiring diagrams that respect the imminent k and the basis element k in some sense. So yeah, so this is just about some background about temporally imminence and temporally algebra. So the result that we are going to use that is relevant to us really is the following, which says that all temporally imminence are non-negative, which is that this function computed at non-negative, totally non-negative matrices is always non-negative. And not just that, if we want to identify an expression like this, which is to be non-negative for all totally non-negative matrices X, then we just have to show that this left-hand side is a non-negative linear combination of temporally imminence. Now there is a nice combinatorial way to identify the corresponding temporally imminence, which is what I'm going to discuss next via this example. So suppose M and N is 4, and suppose I want to identify the imminence corresponding to delta 2, 3, 4, 5 times delta 1, 6, 7, 8. So what do? I basically draw that circle, and I mark the vertices 2, 3, 4, 5 with one color and the other vertices with the other color. And I draw matchings so that there is no intersection between the edges, and the edges also remain inside the convex hull. So this will give us one Kaufman diagram. And so earlier I didn't mention that each of the basis elements in the TN2 algebra identify with certain non-crossing partitions. So these are in fact those non-crossing partitions. So once we have these kind of pictures, these correspond to certain basis element and therefore to certain immanent. So let's call that immanent K1. So this immanent K1 corresponds to this product, and there is only one way to draw these matchings because 2, 3, 4, 5 and 1, 6, 7, 8 are weakly separated. So for example, for another example, if you want to draw look for all immanents corresponding to 1, 3, 4, 5 and 2, 6, 7, 8, there are two ways to draw these matchings. The first way matches with the first one, so we still call it immanent K1 because the color of the vertex is irrelevant here. And the second one, let's call it immanent K2. So this is how we can identify the corresponding immanents for each of the products. And finally, if we want to identify whether the difference of these two products of minors forms an inequality, then we just have to look at the difference of these immanents. And if that difference happens to be non-negatively linear combination, then we have an inequality, otherwise we don't. So in this case we have. So let me now very quickly give a brief idea of the proof. So for that, suppose M and N are 4 and eta is also 4 and I and J are weakly separated. So we choose I to be 1, 2, 3, 4 and J to be 5, 6, 7, 8. And we choose the last element 4 to be the moving vertex in I that switches with the elements in J one by one at a time. And we construct these sets IKR and JKR. So for the first case, we look at the immanents corresponding to delta I, delta J. Now I and J are weakly separated, so there is only one way to draw these Kaufman diagrams. So the red colored vertex is in fact black colored. I've just marked it in red to ensure that to keep track of it as it exchanges its place with the white vertices. So we have immanent K0 for the first delta I, delta J. For the second term, which is delta I1, delta J1, we get two immanents because there are two ways to draw the diagrams. Now note that the first diagram matches with the first one. First diagram for delta I1, delta J1 matches with the first one above. We can so there are two immanents corresponding to delta I1, delta J1. And again, so now to finally verify the first inequality in this expansion, in the system of inequalities, we take the difference of these two and we get that we just get exactly immanent K1, which is non-negative for totally non-negative matrices. Now we keep track. So now immanent K1 is a residue for us that we need to keep track of as we try to identify, prove the second inequality, as we try to prove the second inequality. So the second inequality involves the first two terms that we saw previously and this third term here. So again, we draw those diagrams and we get two immanents, immanent K1 and K2. Immanent K1 is the residue from the previous one. So in computing the corresponding expansion of the immanents, we get negative of immanent K2 here. So there is some telescoping phenomena that is going on here because of weak separability and the way we move the moving vertex. Now, so finally, to identify the next inequality, we again draw the Kaufman diagrams for I3R, J3R, and we do the computation with the residue immanent from the previous inequality, and we get the non-negativity, and the last inequality is the Plucker relation itself. So we don't have to verify that. As we notice that there is some telescoping phenomena going on here as we try to successively verify one inequality after the other. This telescoping phenomena has been there since the inequality due to Ganmacher-Krein and in our papers as well. So, which we completely capture in our result here as by identifying or by discovering Plucker inequalities precisely for weakly separated sets. And now to conclude, because I'm running out of time. I will leave the discussion of the converse for after the talk. Thank you.
Is there a question or comment?
So I'm a bit confused about by imminence. By what I understood by imminence were, if you go back to the definition, instead of what you call fk omega, you would put the character of the symmetric group.
That would be a different
in-
imminent,
So,
I think.
so these what you call temporally leap imminents are not the standard imminents. I mean, for me, those imminents.
So
would-
imminence can be defined for any function on Sn, right? So the one you are referring to
They
are
are
generally called
characters.
character imminents, right?
Okay, I see.
Yeah.
Okay.
Those are also used in proving these inequalities, especially like I think in Barrett-Johnson's inequality by Skandera and Soskin.
I see.
They have used those.
Other questions? Okay, let's speak again. Let's speak again.